Welcome back, everyone. In this series of lectures, we're going to focus on two things. One is how to perform a classification task with TensorFlow. The second is also focusing on how to identify and deal with overfitting through early stopping callback techniques, as well as adding in dropout layers. Early stopping is something we can do with Keras to automatically stop training based on a loss condition on the validation data that we pass in during the model.fit call. Dropout layers are layers that can be added to turn off neurons during training to prevent overfitting. Basically, what we do is each dropout layer will drop or turn off a user-defined percentage of neuron units in the previous layer every batch. So that means certain neurons don't have their weights or biases affected during a batch. Instead, they're just turned off. Okay, so let's see how this all works by heading over to a Jupyter Notebook. All right, here I am at a Jupyter Notebook. I've gone ahead and imported pandas, NumPy, Matplotlib, and Seaborn. And the data set we're going to be working with here is basically a bunch of measurements of tumors and then a classification of whether they're malignant or benign. And let's go ahead and load up this file. We're going to say pd read CSV. And then under data, we're going to load up the file, and it is called cancer classification. So you can tab autocomplete that from the data folder. And as a quick note, underneath our ANNs folder, if you go to the Keras classification notebook and open it up, you should be able to scroll through this and read the entire description of the data set. It contains 30 numeric predictive attributes and then one extra class, and it's a relatively small data set, about 569 instances. So we'll come back here and let's go ahead and do a little bit of exploratory data analysis, and then later on we'll move on to focusing on early stopping callbacks as well as adding in those dropout layers. So something I would always recommend doing is just doing a quick info call, and this will allow you to see if you have any null values right away. And if you scroll through this, you'll notice they're all 569, so none of them are nulls, which is good for us. And then we can also perform a describe call in order to begin exploring the statistical distribution of the various features. And I always like to transpose this just so it's a little easier to read, with the index being the features themselves. All right, so lots of information here we can explore. Let's go ahead and do a little bit of exploratory data analysis through visualization. For classification tasks, it's always a good idea to do a count plot of your actual label to see the number of instances per label and see if it's a well-balanced problem or not. So the label column is called benign underscore 0 underscore underscore MAL underscore 1. So basically it just indicates that benign is 0 and then malignant is 1. So here's the actual feature, or excuse me, label. And then our data frame is DF. We'll go ahead and run that. And this looks to be relatively well balanced. So we definitely have more cases of malignant tumors in this particular data set, but the difference is not extreme here. Then what else we can do is check out the correlation between the features themselves. So you can say DF correlation, and this will actually produce a correlation here. And sometimes what's nice to do is to actually just view this in respect to the label we're trying to predict, which again is whether it's malignant or benign. So we can pass that in, and that just gives us this right here. And in that case, we can then say sort values, and then we can see what is highly positively correlated as well as what's highly negatively correlated. And sometimes it's easier to actually plot this out. And we can do this by simply calling plot with kind is equal to a bar plot. You could also do this with Seaborn if you wanted to. And notice this very last one right here is the actual label itself, which is perfectly correlated at 1. So let's just go ahead and drop that one. So we'll go ahead and say sort values, and after this we'll do the following. We'll say grab everything but the last one, and that will essentially drop that label column. So it looks like we have very correlated values, but very highly negatively correlated. So we should be able to get pretty strong predictions from this data set just based off this analysis here. And we could also do a similar analysis of correlation between the actual variables themselves by calling SNS heat map on this correlation, and this returns a heat map. However, this shows you the correlation with every feature compared to every other feature. And if it's a little small, you can always expand on this by saying PLT figure, fig size, and then choose a larger size, 12 by 12 or whatever you see fit. So that's something you can explore as well. You can also change the color mappings to explore that further. But right now, we'll go ahead and put exploratory data analysis to the side so we can get to our train test split and scaling the data. And then in part 2, we'll focus on creating the model and dealing with overfitting that could occur. So first, let's do our train test split. Our X features, we're going to say df drop the benign column. In fact, I should still have that copy pasted there. And then that's along axes equals 1. And we'll just grab those values so that it's a NumPy array. And then y is going to be equal to df. And in this case, it's just that column, and we'll grab those values. So then we will say from sklearn, model selection, and this should seem very familiar to you by now, the train test split, import that, call train test split, go ahead and expand the documentation string. So you can scroll down here and then grab this example. Let's copy and paste that here. And then what we're going to do is we'll simply change the test size to something a little smaller. Since we don't have that many points, we'll go ahead and change it to just 25% of our data. And to keep things consistent, I'll set my random state to 101. Of course, that's just an arbitrary choice. But if you want to get the same split I do, go ahead and choose the same value. We run that, we get our split, and then finally let's scale the data. We'll do this by using the preprocessing from scikit-learn, and then we will import min-max scaler, create an instance of this scaler, and we will fit transform our training data. So we'll go ahead and say xtrain is equal to fit transform xtrain, and we will do the same for our test data. So scalar transform xtest. Recall, we don't want to actually fit to the test data. We only want to fit to our training data to prevent data leakage. All right, so we did a little bit of exploratory data analysis. There's definitely a lot more you can do, so feel free to create scatter plots, distribution plots, etc., whatever you're interested in. And then, more importantly, we went ahead and did our train test split, as well as the pre-processing to scale the data. So coming up next, we're going to focus on creating the model and then showing you how to prevent overfitting and how to make sure you don't actually overrun on the training data set and then end up having a poor fit on your test data set. So we'll cover all that in part 2. I'll see you there.